Dear students, welcome to yet another class of disconnection approach. This time we'll be dealing with 1,5-difunctionalized compounds, namely also involving Michael addition and Robinson annihilation. So the first example we will be dealing with in this context is the one which predicts or which shows as to in which way we can deal with these 1,5 dicarbonyl disconnection. So the two functional groups are these two carbonyls, as can be seen 1, 2, 3, 4, 5 placed in position 1 and 5 with respect to each other. So this is our target molecule. If this is disconnected between 3 and 4, carbon number 3 and carbon number 4. So it will result in the formation of two synthons, namely one end getting the positive charge and the other the negative charge. The positively charged synthon will be having the synthetic equivalent as shown over here. That is, how can the positive charge be removed? It can be removed simply in the form of H positive, and H will leaving a double bond at that position, so that when H positive leaves, we will be getting the synthetic equivalent as the alpha beta unsaturated ketone. Simultaneously, the other part, that is the other part, because the bond is broken between carbon 3 and carbon 4, so if one part has the positive charge, the other will be the negatively charged part. The negative charge, as we know, can be developed at this end. How? By use, because this is in alpha position to this carbonyl. So this hydrogen here is acidic. It will leave in the presence of a base to create an anion. In other words, we are talking about an enolate. This negative charge moving here as the pi electrons move on oxygen. So what is this? This is an enolate. Enolate. And how can this enolate be generated successfully? If there is an electron withdrawing group present over here, such as an ester, a cyano group, any group which can pull electrons. So generally this is used. So this is the synthetic equivalent for the other fragment. Now, these two synthetic equivalents will therefore react to give us the product. Let's see how this works. The disconnection between the 3 and the 4 carbon leading to this alpha beta unsaturated ketone and this enolate, when it is combined, that is when the synthesis is done. This was the retrosynthesis, the reaction in the reverse. So now when these two react, that is this very active compound which is able to give, because it's got an acidic hydrogen, alpha position to this acidic hydrogen. So this, in the presence of a base, will react within a Michael acceptor. Now yes, the terms Michael donor, Michael acceptor. So this carbene ion which will provide over here, which will be formed, will be the Michael donor, because in the presence of a base, this will leave, hydrogen will leave a negative charge here. So this will act as the donor, whereas this alpha beta unsaturated ketone, because this electron pair pulled upwards, hence as a result of this will move here and this carbon will get a positive charge. So this will accept this. So this electrons from here. So this is known as the Michael acceptor. In the presence of a base, therefore, what will be formed? This compound, which on hydrolysis CO2 will leave, we will get our target molecule. C2H5 and CO2 will leave as a result of hydrolysis, basic, and then heating it in the presence of an acid, and this will lead to the formation of a target molecule. So this was the first example of 1,5-difunctional compound, that is 1,5-ketone dicarbonyl compound, and how we did the disconnection. Now moving on to the next example. Again, this is an important example in this case. Here, as we can see, we have got this is the target molecule, and as has been numbered accordingly, 1, 2, 3, 4, 5. These are, again, this is exhibiting a 1,5-dicarbonyl functionality. That is two functional groups. So this is a two group C disconnection. Carbon bonds are being disconnected with respect to how many functional groups? Two functional groups. In this case, both being the carbonyl. So again, we will be getting, see, this is when it is disconnected at carbon level in between the carbon bonds 2 and 3, we will get these two as our synthetic equivalents. One will be positively charged, the other end, which is attached to carbon oxygen, carbon double bond oxygen, that is an electronegative group, will be negatively charged. So as a result of this, one will be the Michael donor, the other the Michael acceptor. These are the synthons. The synthetic equivalent for this, again, H positive will leave, so we'll get alpha beta unsaturated ketone. And this here will be generated by forming an active methylene compound. So active methylene compound, so it's already got at one end CH2COH. So as esterify it, that is malonic ester, CH2CO, C2H5, CH2CO, C2H5, malonic ester. So that will lead to the formation of this Michael donor. Now the synthesis is simple because these two, when they are, one is the Michael donor, the one which is giving the anion, the other is the Michael acceptor. In the presence of a base, this will turn C negative, this will be C positive, and therefore they will combine to give this product, which on hydrolysis with the elimination of, on heating or elimination of carbon dioxide and ethyl alcohol, will lead to the formation of this target molecule. So these were both examples of our retrosynthesis or the strategies for disconnecting 1,5-dicarbonyl compounds, that is two functional groups we are seeing in this picture, the two functional groups. So this is carbon-carbon two group disconnection. Now this reaction here is clearly showing the use of enamine. Enamine means these secondary amines, where they tend to react with carbonyls. When they will react with a carbonyl, what is formed? An enamine. NH, this N will have lone pair of electrons, so it will attack carbon positive of the carbonyl due to electromeric shift. So this N will give electrons over here, it will attack a nucleophilic attack, addition. So O with H of here, this will abstract this H. So OH, O negative H. OH will be formed, that OH together with H will leave on heating and we will get an enamine. This is an enamine, and so, and this is this formation of this enamine, in this case enamine, formed by secondary amines. This is secondary amine, as we can see. How this reacts further is can be clearly seen because we are using a different strategy this time using this enamine. It will act again over here when we see one as the Michael donor and the other as the Michael acceptor, because this will be forming after disconnection and alpha beta unsaturated carbonyl compound. So this is similar because see, these two are placed, the two carbonyl here, this carbonyl and this was placed in a 1,5 fashion. Now in this way, 1,5 manner. Now this was not disconnected as we did earlier. This is slightly different. That's why I've taken up this example in case you get it in one of the competitive exams. So see, now using the strategy of enamine, when we disconnected, how is this disconnected? Because as we can see, this nitrogen can equally form a bond over here like this. So on disconnection, what will happen when this is disconnected in this way? We will be getting two paths, that is two synthetic, first of all two synthones, then two synthetic equivalents. One is negative and the other positive. Now this one which is negative, obviously this negative charge, because nitrogen has become positive, so it will be balanced. How this charge will go here, so with the result consequently the positive charge on nitrogen will disappear, so we will get this what was shown earlier, that it is equivalent to this enamine. Now this enamine and the other part that has been formed from this by this carbon-carbon disconnection, keeping this mind, now this carbon double bond N, here earlier what was present? Carbon double bond O. That is why enamine is used in place, and that is why it comes under 1,5 dicarbonyl, because this is a reversible reaction. On hydrolysis, once again we will regenerate, because on hydrolysis NH will go away and carbon double bond oxygen will appear here. So this is one part, the enamine, and the other is the positively charged, because the positively charged end will be this side. The negative will be where we have the nitrogen. So this will form an alpha beta unsaturated ketone carbonyl compound. And so this is the synthone, and this is the synthetic equivalent, alpha beta unsaturated ketone. Now the synthesis of this further, because how this can be disconnected further is this can be disconnected or simplified further to, as we can see, what we started from, a secondary amine and a carbonyl compound, this carbonyl compound, because this is the one which will, while going back on in the reverse, will give us this enamine. So let's see the synthesis. The carbonyl compound, when it reacts with a secondary amine, it tends to form, because N will attack this carbon positive over here with due to lone pair. Therefore, it will get a positive charge. This hydrogen will leave H positive. It will attack this O, as OH will be formed. This OH and H will leave and a double bond will be created. That is the enamine. This enamine, when it reacts with an alpha beta unsaturated ketone, therefore this will shift here the electron pair. This will come in this way, and this end will get a positive charge. That is, it will now, one is the Michael acceptor, this is the Michael donor. These electron pairs will come here. These will accept these electron pairs. As a result of this, a carbon-carbon bond is easily formed. And as a consequence of this, once this comes back, therefore hydrogen will add here H positive, and we will get our compound. This compound will be formed. This compound which is formed as a result of this, because these two will react together, this will form, and this can therefore be hydrolyzed and converted back into our target molecule, because this will leave the secondary amine, and over here we will get C double bond O. As this moves here, we will get C double bond O. This is just the reverse of the formation of enamine, which was formed earlier. So this also shows a 1,5 dicarbonyl disconnection. Now let's move on to this example, which is quite common, very useful because it's a very neat and clean reaction, a cyclization reaction. And this follows the two things which we were discussing, the Michael addition and Robinson annihilation, the ring formation. So this our target molecule here, as we can see again, is having a 1,5 disconnection. Now on alpha, and how this will develop, because this bond here, alpha beta, this alpha beta bond, if we break over here, then this double bond will be satisfied how? By double bond oxygen. So one will be negative, the other positive. This will break here, and this will add hydrogen, this will add oxygen. As a result of this, now if we number it, now we have two carbonyls. So we have to first see if we have a cyclic ring cyclohexene with an alpha beta, which can unsaturated carbonyl type, which can disconnect to give us 1,5-dicarbonyl derivative, which can in the reverse, which can form, not derivative, which can form this 1,5-dicarbonyl compound. Then we will disconnect it. So, and let us see now, we will count. So either from either end, so it will be 1, 2, 3, 4, 5, 1,5-dicarbonyl. And as soon as we see 1,5-dicarbonyl, we know that we have in the picture a Michael addition. Michael addition, therefore 1,5-dicarbonyl, one will be a Michael acceptor, the other a Michael donor. So it will disconnect in such a way, because we know we have these two. This carbon hydrogen here will be highly what? This carbon, this hydrogen here, it can easily escape in the form of H positive. Therefore, will be very acidic in nature, and therefore we will tend to form this, from this end we will tend to form the Michael donor. So CHCOET, and the other end which is formed from this is our C6H5CO, that is the remaining portion with the C positive and pH. Now what will the C positive form at the disconnection? The C positive will therefore, a hydrogen will as hydrogen ion, and we will get an alpha beta unsaturated carbonyl compound. So we know now we have the suitable synthetic equivalents for the preparation of our Michael addition. One is the Michael donor and the other the Michael acceptor. So as a result of this, when the synthesis takes place, that is with these two synthetic equivalents, so we will be having these two in place, that is one will be the Michael donor, one will be the Michael acceptor. So because this is alpha beta unsaturated ketone, so this electron pair will be pulled upwards due to electromeric effect. Therefore this carbon double bond will shift here. This end will get a positive charge. On the other hand, this methylene group here, highly acidic hydrogen, so in the presence of a base, this will get a negative charge, and this will therefore tend to form this derivative, that is CH3COCH negative. This we will have over here the C positive, which has phenyl group at one end and CH2CO at the other. And as you can see, this happens together. It's a neat step. I've shown it this way so that you understand. At the same time, H2O from here, and there is cyclization. So it's a very simple reaction and very useful, neat reaction, because there will be total conversion of these synthetic equivalents into the product. So this was our Michael addition, followed by our ring formation or annihilation at the same time. And what we studied today was the two group CC disconnection. Why the two group CC disconnection? Because here we took into account two functional groups. two carbonyl groups which were placed, we can say, at 1 and 5th position respectively with respect to one carbonyl group. The other was in the 5th carbon. If the first was carbonyl was named as carbon number 1, then the other carbonyl was carbon number 5. So together with this, we did Michael addition and Robinson annihilation.